Oh.
It's also written on the board.
There's another camera behind. There's the snap back to you and then we need to yes, location range.
Okay, so today the topic is manifolds. So it's basically a bunch of mathematical definitions. There's nothing very sophisticated about it, and you might think that I'm very bad at teaching physics, but I'm even worse at teaching mathematics. Okay, I'm going to give some examples. You will read the notes. So what are the manifolds? So we want to think about like some curved surface, or like an apple, or a sphere, or potato, and some creatures who live on the surface of this potato, and try to do geometry, to measure, to draw triangles, and measure curves, measure lengths and angles, and this sort of thing. And we want to try to generalize the notions that we have in flat space. In Euclidean geometry, we want to generalize those notions as much as we can to the surface of this manifold, this potato. So the first thing that we can do is try to make maps or charts of this manifold. So try to give labels to different points, the same way that we do it on the surface of the earth. We give names to the cities and to the villages and to the rivers and mountains. So we want to give names to the points, and we are doing mathematics, so we give numbers. So that's the idea of putting some coordinate system or assigning a set of points which uniquely identify different points in this manifold. And then, as in the case of the Earth, we might not want to put a single chart to describe the whole Earth. We can have local maps of different countries, and the only requirement is that if there are two neighboring countries or counties, then of course they want to cover the borders. That's the most important things usually. So they want to cover the borders. So two neighboring countries have maps which cover the borders. The requirement is that when you compare the two maps, when they overlap, they have to agree with each other. So there is no need to have a unique chart or map that covers the whole thing. The requirement is that if there are two, so let me just draw this here. There is this chart number, chart A, and chart B covers another portion of this space. So if they have some overlap, if this region is overlapping between the two, they have to agree in this region. So what is the simple example? For instance, we want to consider a sphere. a two-dimensional sphere that is that sits in three-dimensional space. And then we can think about these maps or charts that give us parameters, different points on the sphere. So for instance, here what I can do is to talk about these charts which are called Fi plus mine, for instance. So there are 6 of them. I corresponds to X, Y, or Z. For instance, I can consider Fz plus. So what is Fz plus? It's a chart that gives coordinates or gives labels to the points in the hemisphere at positive Z. So what it does is that if for any point in the positive hemisphere, Fc of that point would be there is so what is the definition of this sphere? This sphere is defined by the points which have x squared plus y squared plus z squared equals to 1. That's the definition of a two-sphere. And this Fc, what it does is that it takes any point that is sits at x, y, z, where z is also related to x and y by this relation, and it maps it to a point, or gives this a coordinate which is called say x and y, and x is big X and y is big. So basically, it uses the xy plane to determine different points on this sphere. So this is one possibility. Then I can have Fz minus that covers the lower hemisphere, and then we can have a Fx plus. And what it does is that to the point x, y, z, it associates this is Fx plus, it associates the points in the y-z plane, or its projection in the y-z plane. So here there will be, let me call this x1 and x2. Then x1 is x and x2 is y. And then here there will be x1 and x2 in this case, but x1 is going to be y and x2 is going to be z. So the idea is that we should be able to give if you are talking about the okay, so there is some notion of dimensionality of the manifold, like the surface of this surface of this potato is two-dimensional. It means that we need two variables to distinguish different points on it. So that means that it's a two-dimensional manifold, and here these charts, the condition that they have to satisfy is that they give coordinates which consist of two numbers. Now, what other? So now we have assigned coordinates, or we can identify different points on this surface. What other things we do in normal geometry, in flat geometry? We talk about vectors, for instance, or we draw curves. So let's consider a curve on this two sphere. For instance, we can consider so there is charts that just identify different points. Then there are curves. The curves are what? They are just a set of points which are connected to each other, form something like a line at every point. The more formally, they are a curve C is a mapping from R, real set of real numbers or some interval in the interval in R to the full manifold that I showed by M, and it is parameterized by so it's parameterized by a number that sits in R, which sometimes we can call it lambda. So there will be a C of lambda, for instance. So this C of lambda is going to be a point on this manifold. For instance, I can consider a latitude. So latitude is a curve on this sphere, and so what would be how would I write this C of lambda? I can parameterize. So what is the definition of a latitude? Say it's a latitude that sits at some fixed height, z0. Then what it means is that x squared plus y squared is equal to 1 minus z0 squared. Let me define A to be 1 minus z0 squared. Then in this fz plus chart, this latitude is just parameterized in the following way. It's the set of points that are corresponds to x equal a times cosine some parameters. So we said let's choose lambda as the parameter of the curve, and y is equal to a times sine lambda. So as I change lambda within 0 to 2 pi, I go around this curve here. And there is no, of course we could have the same curve, I mean geometrically the same curve, but parameterized in a different way. I could have x tilde, just a different parameterization of the curve to be a cosine 2 lambda and y tilde a equals sine 2 lambda. And of course, we can talk about different curves like longitudes. For instance. There will be lines that go in this way. But then we can talk about vectors. So what are vectors? Vectors are essentially the tangents to the curves. So whenever I have a vector, it tells me that I can make one step along the vector, one infinitesimal step along the vector. So if I have a collection of the vectors, I can make lots of lots of these infinitesimal steps and produce a curve. On the other hand, if I have a curve, I can look at a little piece of the curve and gives me one direction to move. So that defines a vector. However, unlike the flat space, we cannot talk about vectors in a global way because in flat space we can, if you have a vector at one point and a vector at different points, we can always compare these two vectors with each other. Here, on the other hand, these infinitesimal, the steps that we are talking about, they don't live in the same space. They live in something called a tangent space. So one should think about some surface that is tangent at every point, and this is called V, for instance. And the vectors are. So this tangent space is really is a flat surface that is tangent at that given point to our manifold. And then we have the usual notions of vectors in a flat space here. However, we cannot compare them at different points because the tangent space at different points are not the same. Now, if I have a curve, then I can define a tangent vector to that curve. It's just got T mu or T. Then it will have components. So what it does is that formally I can consider this tangent vector to be defined as a map from the space of functions that I define on the manifold to the set of real numbers. So for instance, if I have a curve, what does this tangent vector do? It gives me, so for a given curve, this vector, when acts on a function, it gives me the derivative of that function along the curve at that given point. So now we said that we have assigned some coordinates to our manifold. So when we talk about the function that lives on a manifold, what is the function? The function is a map from our manifold to a set of real numbers. In particular, when I consider a chart, then I can give the coordinates, this set of coordinates to the function, and this function assigns to those set of coordinates, say in this case of two-dimensional manifold, this f is a function of two variables, which are coordinates of the points on the manifold. It's a function of two variables, so it takes these two variables and gives a number which lives in R. Now, when I take the derivative with respect to lambda, the parameter of the curve, I can just use the parametrization of the curve in this same coordinate system and the chain rule to write it as dx1 d lambda times d1 of f plus dx2 d lambda d2 of f. And this is true for all functions F. Therefore, what it means is that that was our definition of T. But since this is true for all F's, we can just say that T itself can be expanded in terms of partial derivatives. So T can be written as T mu times D mu, where T mu is given by dx1 d lambda and dx2 d lambda. So for instance, in this case, when we parameterize the curve by, in the case of a latitude, we have T mu for a fixed latitude d0 is given by minus a sine lambda and a cosine lambda. And now you can see that if I consider the other parameterization, the tangent vector changes by a factor of 2. Okay, of course, now one can ask what are the connection between components of vectors if we have two charts that are overlapping with each other. And the relation between components is exactly what you already know. That is what is inherited from this description of vectors, or this expansion of the vectors in terms of partial derivatives. So we know that as I go from one chart to the other, then what happens to the vector is the usual transformation law of the vector. And that's what we were traditionally defining the vectors, any object that transforms according to the transformation law of tensor. So that agrees with the more formal definition. And of course, now we can define other objects in the tangent space. Again, as before, we can talk about tensors that have multiple indices, and then they have tensor transformation laws. For a general T mu nu alpha, for instance, the one definition would be the old definition, that any object that transforms according to the transformation laws of two well, maybe I should first talk about covectors, then talk about that. So we can, well, so we can talk also about maps from vector space to the real variables. And these are called covectors. So what they do is that they take a vector and they give a number. So remember, vector would take a function and would give a number. Covectors take a vector and give a number. And we can define them by expanding them in terms of a basis. So we can define some basis of covectors which are called dx mu, and define by saying that when they act on the basis of vectors, they give delta mu nu. And then a general covector will be written as omega nu dx mu. It will be written in terms of this basis. And if it acts on a vector, what it does is that it gives me a number which is the sum of the omega mu v mu. So this is basically what we used to call a covariant vector. So it has to give a number which is therefore independent of what chart or coordinate system we use. And that fixes the transformation property of omega. Omega mu is dx mu dx prime mu times omega prime mu. And then the space of these objects are called sometimes called V star. So omega belongs to V star, the cotangent system. Any questions so far? Yeah, I agree. There is nothing very deep about this. There are just some definitions. Okay, so now we have vectors and covectors. We can also talk about tensors. And then what the way they can be defined as linear maps from the. So this will be something that acts on a bunch of vectors and a bunch of covectors and gives a number. So it can be defined formally in this way. So if there are n indices here and m indices here, then it is called a rank nm tensor. So these n indices act here. And then there are of course objects that transform according to the usual tensor transformation. So for instance, d mu nu alpha, when I go from one chart to the other, is going to be dx mu, dx nu, dx prime rho, dx prime sigma, dx prime beta, dx alpha times t prime rho sigma beta. So again, anything that behaves like this, that we will call it a tensor. Or more formally, any map from the from m objects in the tangent space and n objects in the cotangent space to R.
Right. That's
Yeah.
geometrically, that means like what is the covector space?
What is the covector?
Symmetrically, if the vector lives in the tangent space, what is like geometrically the cotangent space?
What is the geometrical? Well, if you embed your manifold in some higher dimensional space and then think of the tangent space as as a plane. So if you think of the tangent space as a plane, that is a plane that is tangent to your manifold at a single point, then so this plane is just a Euclidean plane, right? And there in Euclidean space, the mapping between the vectors and covectors is trivial. You can just because your metric, the Euclidean metric, is just 1, 1, 1. So at the level of these pictures, I cannot draw anything different for covectors. So you could ask the same question on a flat surface, on the Euclidean surface. So what is the space that covectors live in? There is a one-to-one map between the covectors and vectors, as I'm going to say, when you have a metric. In Euclidean space, we have a metric, the Euclidean metric, that allows you to make a one-to-one map between vectors and covectors. So usually, even when we talk about covectors in Euclidean space, we don't really distinguish. We talk about the analogous vector, the dual vector of that covector.
So there is no that.
That's not that I know. No.
Okay.
Maybe there is. I don't know.
Okay.
These covectors are equivalent to the one forms, right?
Yeah.
And I read it in a book that geometrical picture is like a projection in a surface, the tangent vector. I mean, when you take a one form and a vector, it gives you the projection. That's the scalar product. I think I saw it in a book written by Gray that gave the geometrical picture of the one forms. Like surfaces, or I don't remember it exactly. The book.
Well, one thing that you can do is the following. The same way that we talked about vectors as being the tangents to the curves.
Yeah.
So any curve is going to define a set of vectors for you, which are tangents at different points. So at any point that it passes, it assigns a vector. And Now you can also consider a function on the manifold, and that function has some levels, which are the lines along which the function is constant. So I have some f of x, like that. So when we talked about latitudes, I can talk about the function which is f of the f of x1 and x2, or let's call them x and y. Any function of x and y which only depend on the x squared plus y squared. Say it is f of x and y is x squared plus y squared. Right? So consider this function on the sphere, and this is x and y. So then, if you want to consider lines of constant f, these are actually the latitudes, right? Now, given a function on the manifold, that you can find also that function gives you a covector. So that is basically a covector omega mu, which is defined as d mu of f. The gradient of your function. That is a covector. So the same way that a curve gives you a vector, a function gives you a covector. Now when you take the inner product, or when you talk about omega of v, let's say I have some curve on this manifold, C. And then these are lines of constant f. When you combine omega with the tangent to this vector to this curve C, that tells you that as you move along C, how much the function is changing. Because this is nothing but Tc mu times d mu f, and Tc mu is just dxc mu d lambda times d mu. Which is df d lambda.
So the concept of the covector is like similar
to gradient.
That is the right. That would be the gradient of it.
Yeah, this is a gradient.
And the vectors is
tangents to the curve.
Tangents gradient. Okay.
If you're interested in nice geometrical interpretations, one place to look at is Misner-Zornwiller, but it's a really thick book. So it's up to you if you want to look at it. Okay, so we can also have vector fields and tensor fields, which are not members of the. So when we talk a field, it's like a quantity that exists everywhere on the manifold. So a vector field is the assignment of a vector to every point on the manifold. Then you will have an index. You will have a there will be a V of, in these two dimensions, a V of x1 and x2. For instance, if we consider the collection of the tangents to all latitudes, that gives us a vector field on the sphere. So remember we said that if we consider some specific latitude, then the tangent is going to be minus a cosine lambda, sine lambda, and a cosine lambda, where a was square root of 1 minus d0 squared. So that was the latitude that lives at a specific z. Now, let me just change my let's see, what do I do? And then we had the relation that x1 is equal to a cosine lambda and x2 is equal to a sine lambda. And here a was the square root of 1 minus d squared, which was also just x1 squared plus x2 squared, right? So what I can do is that from here I can find cosine lambda and sine lambda in terms of x1 and x2. So cosine lambda is just x1 divided by a, which is the square root of x1 squared plus x2 squared. Sine lambda is x2 over x1 squared plus x2 squared. So I can consider the collection of all of these latitudes, and then that collection gives me the field, the vector field, which is defined as so this is now T, which lives at there is the assignment of this vector field at every point on the manifold. And if I just plug in these values there, I get minus x2 and x1. Sorry, the indices I put it down. So x2 and x1. So what is it? It's just a collection of vectors at every point on the manifold. Okay, so there is a very important tensor field, which is called a metric. You already know. It's something that we need if we want to talk about distances. So basically, when we talk about almost any local local geometrical constant we need to use the metric key. It allows us to measure the lengths or the angles between different vectors. So this is a rank 2 covariant tensor, so it takes two vectors v and w and gives us a number. If we have so if you have the generalization of the Euclidean geometry, they are called Riemannian, then this is also positive definite. So for any two vectors, it gives us a positive or non-negative number. But when we talk about Lorentzian, then it will be it can also be negative. So it is a rank 2 covariant tensor, so we can, in a coordinate system, we can write it as G mu nu with lower indices with the usual transformation property. And then what it does is that it allows us to measure lengths. So, or we can measure the distances. So one thing that I can do here is that if I have a curve between points A and B, then I can use this metric to measure the distance along the curve. And that would be just taking the integral d lambda, the square root of g mu nu times t mu. So that would be L A B along the curve C. Then we can ask, for instance, what is the curve with the shortest length between the 2 points? And that is something that we have been asking before. These are called geodesics. This is exactly the object that we were writing for a point particle. And this is what we call the action for the point particle. We would extremize this action. Extremizing means that we want to find a curve with the shortest or longest length. In the case of Euclidean geometry or Riemannian geometry, that we can ask about the shortest length. So there will be a shortest length path. In the Lorentzian case, we would find the longest length as the geodesic. But anyway, the curve that satisfies, that extremizes this, that is called the geodesic, and then it satisfies the equation of motion that we encountered before, the geodesic equation. Okay. So let's then talk about embedding, which allows us to do some more concrete examples. Embedding. which is something that I already used to define to talk about a sphere. It makes it always easier to think about the manifold as being embedded in some higher dimensional manifold, especially if especially embedding in Euclidean space, in flat space, or a space-time. That would make thinking about curve geometry much easier. Of course, the point of finding this using this coming up with this more abstract machinery is that you don't have to do embedding. So we introduce this extra tools so that we can talk about manifolds without having to talk about embedding. But it's useful to consider examples so that we get some intuition. Okay, so again, let's go back to our sphere, which is embedded in higher dimensions, and talk about the metric. So when so we already said that we can talk about embedding of the manifold. That's just saying that the manifold, define your manifold as a function in the higher dimensional space. So for instance, in this case, we are talking about the function of the sphere is defined as the function of x by z equal to 0. That is our definition of 2 sphere. And that function is nothing but x squared plus y squared plus z squared minus 1. That is the thing that is equal to 0. Now then we can come up with different coordinate system that cover the sphere. So I talked about these projections into different planes. Another coordinate system that is useful is to do the projection instead of doing the just looking at the xy coordinates, to sit at one of the poles, like the north pole, and do stereographic projection, which is to assign to every point. So I'm sitting here, that's my pivot point. And then to every point on the sphere, I assign a point on the surface. So this is a 2 sphere. This is supposed to be a plane. And then there is this sphere which lives on this plane. And this stereographic map assigns to every point the projection of this point on the plane as seen from the point on the North Pole. So let's see how it works more explicit. So we can this is again x, y, z. Okay. We know that a point on the sphere, we can use the spherical coordinates to assign to it a spherical coordinates theta and phi. And then we can ask what would be this new coordinates. So what would be, let's call them, what do we call them? Let's call them Z1 and Z2. So let's first ask what is Z1, Z2 divided by Z1. So can you tell me what is Z2 divided by Z1 in terms of theta and phi?
It should be the tangent of the angle with the x-axis.
And that's phi.
That's phi.
Yeah. So it is tangent of phi. And then if I also know what is Z1 squared plus Z2 squared, then again in terms of theta and phi, then I would be able to complete this mapping or this chart to assign a value Z1 as a function of theta and phi and Z2 as a function of theta and phi. So what would this be?
Okay, that would be the projection in the xy plane, and then take a projection in the x plane and the y plane, and then square them plus and add them. That's it. So that would be
give me a formula.
sine theta and cosine phi, and sine theta and sine phi, and then square them and add them.
So what is the answer?
Okay. Wait. It's sine squared
You
theta.
cannot do it in your head.
Sine squared theta.
Sine squared theta. So let's see. Let's consider a specific point. So theta is this angle, right? So as I send theta to 0, I come closer and closer to this point.
Yes.
So let's see where Z1 and Z2 go as I come closer
Oh yes,
to
there
this
should
point.
be a.
They go, so let's draw a couple of them. This is here. If I come to a smaller theta, I go here.
Yes. Okay.
So that goes to infinity.
Yes.
As theta goes to 0. Sine squared theta goes to 0, so it cannot be that.
Yes. Yes.
So is the definition clear?
Okay.
Okay. So there is a surface. There is a ball on this surface, or a sphere on this surface. I'm sitting at the top of this, on the North Pole. And then I want to assign coordinates to different points on this sphere. So I take one particular point. I'm sitting at the top. And what I do is I draw a line that connects that point to North Pole. And then I continue it until it hits the surface, the 2D surface. So the coordinate of this point will be the coordinate of that point that the line hits on the surface. So it's well defined and it is unique. For every point on the sphere, I get a unique point on this bottom surface. Now my question is that take the point on the sphere that is parameterized by has coordinate theta and phi, and tell me what is the coordinates on this 2D plane.
Okay.
It's just a trigonometry problem.
What is theta there? Is angle.
Angle with the z-axis, yes. So z is equal to cosine theta, and x is equal to sine theta cosine phi, y is sine theta sine phi.
So theta 1, theta 2 are in the same triangle?
Are what?
Are the same triangle?
Which one?
Theta 1, theta 2?
Well, no, Z1 and Z2 are just the pairs that identify every point.
Okay.
Are just components to the two coordinates on this two-dimensional on this surface. So Z1 and Z2, I can draw the axis. So this is Z1, this is Z2.
Okay.
They are parallel. Z1 is parallel to the x-axis and Z2 is parallel to the y-axis.
Okay. Okay.
That's why we had this relation.
And X, Y, and Z are defined in the center of the...
Yeah.
Okay.
minus it. This tangent find out inverse of 1 over the tangent.
1 over
The tangent of theta square.
that's called tangent.
Yeah, yeah. Tangent square.
And that's this f.
Yeah.
Let's see. So if I send theta to 0, it becomes cotangent of 0, which does go to infinity. And if I send theta to pi, it becomes cotangent of pi, which is 0. So that it satisfies at least those sanity checks. Is there any other good check?
Maybe pi half.
Mm-hmm. But it's not that obvious by what it should. Or pi.
Should be 1.
So if theta is pi half.
No, sorry, I consider my sphere different. Remember. Sorry, my answer is 1. When the plane is in the center of the sphere.
Oh.
Yeah, I misread the wrong.
Uh-huh. So what should you expect if theta is pi over 2? Do we have any expectation? What is this angle when theta is pi over 2?
Pi by 4.
Yeah. So let's call this angle beta. Well, we can even determine beta as in general. What is beta as a function of theta?
Sorry?
What is beta as a function of theta?
Could be 18.5. Pi minus theta over 2.
Pi
minus theta over 2. Yes. Because these two legs are the same. So this is beta, therefore this is 2 beta. So 2 beta plus theta is pi. So this is beta. What is this length?
Which one?
This length. So this length is 2. And beta, we know what it is. So what is this length?
From 10.
2 tangents.
Yes.
So
2
this
divided
is
by-
exactly f of theta, the square root. The square root of f of theta. Remember, f of theta is just this length, or r. Let's call it r. So this is r squared. R of theta is 2 times tangent
Tangent of theta.
tangent of beta, which is 2 times tangent of pi over 2 minus theta over 2, which is 2 twice cotangent of theta over 2. So it was close up to factor up to 4.
Yeah.
Okay, so what can we do with this embedding? This was an embedding. I was just defining this stereographic map. Now, when I have embedding, I have some embedding space which has its notion of length. It's Euclidean space. On Euclidean space, we have Euclidean metric. We know how to calculate lengths of a line in Euclidean space. That induces a metric on our manifold. So if I draw a curve on this manifold, I can assign a length to this manifold by asking what is the length of that in the embedding space. So how do we do it? Which means that at the end of the day, I can define a metric, an induced metric on this line. And the way we can do it is that once we have a coordinate system, like this theta phi coordinate system, we can determine what is the elemental length that is induced on the sphere. So what we used to call ds squared for S2, which is induced from the embedding space. So we know that the embedding, so let's first go to ds squared of the embedding space, which is just R3. That is dx squared plus dy squared plus dz squared. Now we know that if we consider some little length element on our sphere, which corresponds to some d theta and d phi, some small displacement, that uniquely determines how I move in the embedding space. In other words, a curve on the manifold also defines a curve in the embedding space. And a vector in the manifold defines a vector in the embedding space. So given d theta and d phi, I can calculate dx, dy, and dz. So what would they be? dz is just sine theta d theta. Dx is cosine theta cosine phi d theta minus sine theta sine phi d phi, and dy is cosine theta sine phi d theta plus sine theta cosine phi d phi. I can just plug this in there to get ds squared, the induced ds squared on the manifold. So the length of this little displacements on my manifold, which is induced by the length element in the embedding space. So if I just plug these things in there, not surprisingly, what I'm going to get is d theta squared plus sine squared theta d phi squared. So this defines my metric in this theta phi coordinate to be, so it's a 2 by 2 matrix. So it is 1 and sine squared theta 0, 0. Now we have a different coordinate system, this z coordinate system. G is a tensor. One can ask what is the metric in this new coordinate system, which is left to you as an exercise.